unveil the notion of symmetric key cryptography. This is a concept where a single identical key is utilized for both the processes of encrypting and decrypting data. To truly understand its importance, it's essential to delve into its historical roots. Symmetric key cryptography is not a product of modern times. Historical records show that it was used as early as the time of Julius Caesar for protecting sensitive military information. Now, fast forward to the present day, and we find its applications have only expanded. It safeguards our online transactions, secures our email communications, and even protects the data on our smartphones. So it is evident that symmetric key cryptography, where the same key is employed for both encryption and decryption, has always been and continues to be a cornerstone in the realm of modern-day security. Let's delve into the foundational principles that bolster symmetric encryption, a system that is of immense significance in the world of cybersecurity. At its core, symmetric encryption involves two primary methods. The first is substitution, which is the process of replacing individual elements of the plaintext with different characters, symbols, or groups. The second technique is transposition, a method where the positions of characters in the plaintext are systematically rearranged to create the ciphertext. Now, let's touch upon the crucial aspects of symmetric encryption, namely key length, key generation, and key distribution. The key length is a critical parameter as it directly ties with the strength of encryption. The longer the key, the harder it is to crack. Key generation and its distribution, on the other hand, must be done securely to avoid any possible interception by adversaries. Unquestionably, these aspects play a vital role in maintaining the integrity of symmetric encryption systems. Dive into the Data Encryption Standard, DES, as a historical encryption standard. DS, developed in the early 70s by IBM and subsequently adopted by the National Institute of Standards and Technology, NIST, was once the gold standard for data encryption. It operates by using a 56-bit key to encode blocks of 64-bit data, employing a complex structure that includes 16 stages of computation. At the heart of DES lies its infamous Feistel structure, named after the German-born physicist and cryptographer Horst Feistel. This structure divides the data into two halves before mixing them with the encryption key, achieving a good level of security. However, with the rise of more powerful computing technologies, the 56-bit key used in DES was proven to be insufficient, rendering DES vulnerable to brute force attacks. This vulnerability is the primary why DES is now largely deprecated. Despite this, DES played a crucial role in the evolution of encryption standards, paving the way for more advanced methods. Enter the Advanced Encryption Standard, AES, the successor to DES. AES was developed at the turn of the century to address the inherent vulnerabilities in DES. It provides a more robust security framework, utilizing key sizes of 128, 192, and 256 bits, and encoding data in 128-bit blocks. This increased complexity makes AES more resistant to attacks than its predecessor. In comparing DES and AES in terms of security, performance, and widespread adoption, it is clear that AES comes out on top. Its enhanced security features, combined with its ability to handle larger blocks of data, make it a superior choice for modern data encryption needs. Despite the historical significance of DES, it is AES that stands as the current standard in data encryption. Compare DES and AES in terms of security, performance, and widespread adoption. Explore different modes of operation for symmetric key algorithms. In the vast universe of cryptography, these modes are pivotal in ensuring the integrity and security of data in transit. Let's start with the electronic codebook, ECB mode, the simplest form of encryption. Its primary strength lies in simplicity, making it easy to encrypt and decrypt data. However, its main drawback is pattern recognition, where identical plaintext blocks produce identical ciphertext blocks. Next, we delve into the cipher block chaining, CBC mode. This encryption mode, unlike ECB, adds a layer of complexity by intertwining each block with the preceding one. This procedure eliminates pattern vulnerabilities, but it is not without its own flaws. If an error occurs in one block, it cascades, affecting the deciphering of subsequent blocks. Lastly, we have the counter CTR mode. Instead of chaining, CTR uses a counter to create unique block ciphers. Its main advantage is parallelization, speeding up the encryption process. However, its weakness lies in its reliance on a counter, which must never be reused with the same key. For every mode, we have explanatory examples and engaging illustrations to aid your understanding. These visuals not only elucidate these complex concepts but also make them memorable. Provide examples and illustrations to aid understanding. Summarize the advantages and disadvantages of symmetric cryptography. This technique's speed and efficiency make it popular for multiple applications. It processes data quickly and requires less computational power than other methods. However, it does come with issues. A major one is key distribution. Securely sharing the key is a significant challenge. Another concern is its vulnerability to brute force attacks, as it can be cracked if enough computational power and time are invested. Address vulnerabilities like key distribution challenges and susceptibility to brute force attacks. Let's now revisit the crucial topics we've dissected throughout this lesson. We began by understanding the concept of cryptography, the science of encoding and decoding information. We then dived into the fascinating world of symmetric key cryptography, an efficient and crucial method used in securing data. We explored its functioning, how it utilizes a single key for both encryption and decryption. We discussed its advantages such as speed and efficiency, and its shortcomings such as key distribution issues. Finally, let's reiterate the immense significance of symmetric key cryptography in securing data.